Alright, today we're going to continue our lectures on covalent bonding. This will be covalent bonding part 2. If you remember, in part 1 we kind of defined what a covalent bond was, where you have two atoms sharing electrons. And in this case we're going to continue with that, except we're going to learn how to draw that either using what's called electron dot structure or Lewis dot structure, or using structural formula. And so we're going to learn the basic principles and rules governing that process. If you remember, there are three types of bonds. We have a single covalent bond, which is two shared pairs of electrons, one shared pair, which involves two electrons, and a double covalent bond, which is two shared pairs or four electrons, and then a triple covalent bond, which is three shared pairs or three electrons. And as a reminder, it's always the unpaired electrons of each atom that are involved in the bonding process as we go on. So we're going to start with a very simple atom, and we're going to start with what we all know as H2O. So if we have something like this, if we had H2O here, and we wanted to see, well, how would this bond, what kind of bonds, single bonds, double bonds, triple bonds, would it form? We first need to determine one very important thing, and that is what we call the central atom. If we don't have a molecule, that is what we call diatomic molecule, which would be something like oxygen bonded to itself, so O2, nitrogen, N2, hydrogen bonded to itself, H2, where an atom bonds with itself, then you have to find what the central atom is, such as in this case. What is everything else going to bond to? So the easiest way to do that is find out which of the two atoms can form the most bonds. So in this case I only have two different elements. So I have oxygen and I have hydrogen here, and I'm going to take a look at how many valence electrons they have and how many they need in order to complete their valence shell. Oxygen has 6 valence electrons, and therefore it needs 2 to get to 8. So it can form a total of 2 bonds. It may not form 2 bonds. It may only form 1 double bond and therefore get to 8. But it has the potential to form 2 bonds. So I'm going to write 2 down here. Hydrogen has 1 valence electron, but it only needs 1. So the maximum amount of bonds it could form is 1. So I take a look at these. I have oxygen, which can form 2, hydrogen, which can form 1, and the one that I'm going to choose is always going to be the one that can form the most bonds, and that will function as what I call my central atom, which in this case is oxygen. So that's my determining factor, basically, as I choose which one's going to be my central atom. So as I come over here, what I'm going to do then is I'm going to draw oxygen here as my central atom, and I'm going to put it right here. Here's oxygen, and I'm going to draw it with its dots. So here's my electron dot structure, or Lewis dot structure. It has 6 valence electrons, so 2 of those are paired electrons, and then I have 2 that are in the other orbitals that are unpaired electrons, and those are going to be the ones that are involved in the bonding process. And then I'm going to have hydrogen, and so I have my hydrogen atoms, and I use their symbol to draw that, and they all have 1 valence electron, and you notice I'm using a different color to represent them so I can tell which electron belongs to which. And I draw my other hydrogen over here, and here's my dot for it. And you'll notice what happens here is I end up with hydrogen, and its octets are completed, or duets, excuse me. Here's one duet, so that hydrogen is taken care of. Here's the other duet, and that hydrogen is taken care of. And then if I take a look at, so these each have 2 electrons, so there's 2, and there's 2 electrons there. So those are for the hydrogen, so those duets are completed. And then, of course, those also count for the oxygen. So if I'm trying to see, have I completed my octet for my oxygen, I have those 2, so 2 plus 2 is 4, and then I have the original electrons around the outside, 2 here and 2 there. So if I look, there's 4 2s, or a total of 8 electrons. And so oxygen's octet is completed. And so all my duets and octets are completed, and everything's happy and content. They're stable now. So that's the way that I would draw. I don't need to draw all of the, I can get rid of all of the different things here. All I would need is the, oops, we erased something we didn't need to erase there. All I would need in this case would be the dots. That's how it would look in its finalized form from there. Another way I can do this is if I go back and I had oxygen again, and I don't need to worry about the dots as much here to begin with. I know I'm going to form single bonds with hydrogen, so what I can do is use what's called structural formula. And in a structural formula here, instead of writing H2O or showing the Lewis dot structure, I can just write a dash, and that dash represents 2 electrons, or a single bond, one shared pair, and I can show what 2 elements or what 2 atoms they're in between. And then I would also want to write my, if I have any, I want to write my valence electrons that are around my central atom, which in this case I do have some, and that will become important a little bit later in another lecture where we talk about shapes of molecules and determining that. So right now we just want to make sure that we put them in. Remember that each of these lines right here, that represents a pair of electrons, and so that's what I want to focus on. So I'm not going to worry about, I have the 2 lines there which are each a pair of electrons, so that's a total of 4, plus my other 4 around oxygen, so that's a total of 8 valence electrons, and so my octet is complete. So that's called structural formula, and that's another way to draw it as well. So let's do another atom that maybe involves something a little bit different. Let's say we have something like carbon and some hydrogens again, and let's say sulfur, just for something a little bit different. And again, I'm kind of making these up as we go along, just so you can see how different things bond. So let's say we have something like this. These are all non-metallic, or non-metals, and so it's going to be a covalent bond. So again, I have 3 different elements, so I need to figure out, well, which one is going to be my central atom. So I'm going to write them out here. I have carbon, I have hydrogen, and I have sulfur. And carbon, hydrogen, sulfur, and we said that want to figure out how many bonds they can possibly form, and that is always based on how many electrons they have and how many they will need. Carbon has 4. It needs 4, so therefore it can form a potential of 4 bonds. Hydrogen has 1 and it only needs 1, so it can form a potential of 1 bond. Sulfur has 6 valence electrons, and therefore it can form a potential of 2 bonds. So once again, as I'm looking at this here, I see that it is carbon that can form the most bonds in this case. So carbon is going to be my central atom. So as I move on here, I'm going to go ahead and I'm going to draw carbon. So here's, let's erase that, if I can do that. And here's carbon, and carbon has its valence electrons. It has 4, and so it looks something like this. And then I want to draw, in this case, the hydrogens in. Why do I want to do hydrogen first and not sulfur? Well, basically the answer to that is simply this. I want to form the easiest bond that I can form first. Take care of that first. It's kind of a simple basic principle to operate off of. How would I know that hydrogen is my simplest bond? Well, I know that hydrogen only needs 1, so the only bond that hydrogen can form is a single bond. It can't form a double bond because a double bond would require hydrogen having 2 or more electrons to share. And it definitely can't form a triple bond either. So I'm going to start, if I can form a single bond and satisfy a duet or an octet, then I'm going to do that first. So here we go. I have hydrogen here. Here's hydrogen's valence electron. I had 2 hydrogens, so here they are, both of them, and they're bonding with carbon, and that satisfies both of their duets, as you see there. And it also gives carbon, it helps carbon out. Carbon had 4, now it has 6, as it shares those 2 with hydrogen. So carbon now it's closer to 8, but it's not at 8 yet. And so the only thing left that carbon has to bond with is sulfur. And as you take a look at both carbon and sulfur, now both of them need 2 valence electrons. Well, how convenient. We have 2 valence electrons here that carbon has to share. Oops, we deleted something here. Sulfur has 2 to share as well. So we're going to draw in sulfur here. We'll find a new color here for sulfur. So here's sulfur. Sulfur has its valence electrons on the outside here, and then it's got the 2 that it's going to share because it's going to form a double bond. And so we've got our double bond here with 2 shared pairs. 2 of those electrons coming from carbon, 2 of those electrons coming from sulfur, being shared in the middle. And now if we were to count our electrons that belong to each atom, we should have carbon and sulfur should have an octet, and hydrogens should have a duet. So we have the 4 here that belong to both sulfur and carbon, and then the 2 or the other 4 that are around sulfur. So that's a total of 8 for sulfur. And then you have the 4 again right here for carbon, and then you have the 2 by each hydrogen, and again that's a total of 8 valence electrons for carbon, and then you have the 2 hydrogens which have their duets, and so that is complete once again. And we could do this, like we said, another way as well. We could take carbon, draw it, and we could start with our hydrogens and draw a dash showing a single bond to them. We call this a structural formula, and then 2 dashes to sulfur showing a double bond, and that would be how we draw our structural formula. And since there are no other, since all the electrons are used up around carbon there, we don't need to draw any electrons above carbon. Each dash represents 2 electrons, and you see you have 4 dashes for a total of 8 valence electrons around carbon, and that would be how the structural formula looks. And sometimes the structural formula is kind of handy when we're trying to determine the shape of a particular molecule. So that would be the 2 different ways we could draw this particular molecule. Let's do one more just for practice. Let's say we had something along the lines of let's say we had something along the lines of this substance right here. And we wanted to know, well, okay, we've got 3 different atoms here again, or 3 different elements. Which one is going to be our central atom? So we have hydrogen, we have carbon, and we have phosphorus, which is my central atom. Hydrogen has 1, it only needs 1, so it can form 1 bond. Carbon can form 4 bonds because it needs 4. Phosphorus has 5 valence electrons, so it only needs 3, so it can form 3 bonds, or it has the potential to. So again, we can see that carbon is going to end up being my central atom. So as I come over here and I begin drawing it, here's carbon, and I'm going to draw my valence electrons. It's going to look very similar to what we last drew here, and then I'm going to have my hydrogen here, and I'm going to complete its duet. Remember, I'm going to start with hydrogen. Why? Because it has the simplest bond to form. That's a single bond. It only needs to share 1, so I'm going to take care of that first. Otherwise, it becomes a little more difficult to figure out, well, what's what. So start there, and then I only have one other thing left to bond to carbon, and that's phosphorus. And phosphorus needs 3, and if I look now that I'm sharing with hydrogen, I now have 5 for carbon, meaning carbon only needs 3 as well. What a coincidence. And so if they both need 3, the only type of bond that will satisfy that is a triple bond. And so I'm going to have to, each atom is going to have to share 3 electrons. So carbon's going to have to share 3 with phosphorus, and phosphorus is going to have to share 3 with carbon. And so I'm going to get phosphorus over here, and we'll draw a phosphorus here. And so phosphorus is going to have 2 on the outside here, and it's going to have 3 here. And we're going to redo this one here. Actually, let's see here. Erase this guy, and we'll do this right here. We'll move him over here, and so now we have 3. Actually, you know what? I don't like how that's written. Let's redo this whole thing. It's kind of sloppy. Let's tidy that up. So here we have our valence electrons. And there we go. We have our valence electrons, and so in this case you can see in the middle between phosphorus and carbon there are 3 shared pairs, or a total of 6 valence electrons, what we call a triple bond. And if I want to count again and see, are my octets complete, I have my 6 valence electrons here that belong to both carbon and phosphorus. So 6 here and 2 here for phosphorus, and then again I have 6 here and 2 here for carbon, so 8 there as well, and then of course the 2 that belong to hydrogen. So my octets and my duets are complete, my molecule is stable, it's lost energy, I'm good to go. And of course we could draw this again that same way, using structural formula. Carbon here for my single bond with hydrogen, and then my triple bond with phosphorus. And that's another way that I could draw this as well. Call that structural formula. So that's the way in which I can draw, and the principles by which I follow. And it's very important to determine which one is your central atom first, and then start with your smallest bond, or your single bonds first, if you have any, and then go to double bonds, and then lastly go to triple bonds if you have any. That's the easiest way to go about drawing these, and we'll practice this in class.